Hello, everyone. My name is Roy, the Business Development Manager in charge of UK and Ireland region. First of all, thank you very much for joining the webinar today. And I hope this session will be informative and insightful for all of you. So as you already know, today's webinar will be a technical talk and project applications of integral abutment bridge by one of our major clients, AECOM. So before starting the webinar, I will just have like 5 minutes to introduce about our company Midas and also regarding the webinar. So our company Midas is an engineering software publisher and developer since 2000. The headquarters is in South Korea, and we do have many branches over the world, such as UK, Poland, US, India, China, etc. And there are numerous Midas clients over the world with different fields, such as bridge, buildings, geotechnical, or mechanicals. So for bridge, you know that we have Midas Civil and FENX. For buildings, we have Midas Gen and Design Plus. For geotech, there is a GTS NX and Soilworks and NFX and FX Plus for mechanical. And for today's project application, Midas Civil will be used, and at the end of the session, the new updated Midas Civil, which we called the new Civil NX, will be introduced shortly. And you will see the big changes compared to Midas Civil during this webinar. So yeah, to introduce our speaker today, one of our best Midas users in UK, who is from who is proficient in bridge engineering, the Andrea Caristo from AECOM, will be sharing you about his project done using Midas Civil, and our best technical support engineer in Midas, Manoj, will be joining Andrea to technical talk and to present to you about our new Civil NX. Trust me, I had their presentations earlier, and you will get lots of insights from their bridge engineering experiences. So the agenda will be followed by introduction of the speaker, Andrea, and his project, and the introduction to integral abutment bridge and brief literature review with using Midas Civil. Also, there will be an introduction of the new Midas updates, which I said Civil NX. And at the end of the session, there will be a Q&A with the participants at the end. So there will be a Q&A at the end of the session, but please feel free to leave questions in the advance during the presentation if you have any queries, and we will reply on each of your queries. To ask the questions, you will find the chat box as shown in the screen here. And of course, we welcome your questions by email also. So here is our email address, uksupport@midasuser.com. And lastly, just to share you about our current offer, we are currently having an end of first half promotion until June to all the webinar registrants. There will be some special discounts up to 30%, also free additional licenses and free customized consultations or trainings regarding your actual projects. And especially for UK clients, we are visiting UK from 4th to 13th June to meet our clients. And we are happy to visit your office to provide some free technical CPD sessions with any topics or even regarding your actual current project as well. So if you have any difficulties or interested in after this webinar, yeah, please feel free to contact us. So here's my contact to reach out. You can reach either to uksupport@midasuser.com or royhan@midasit.com. So thanks for your attention, and now we will start our webinar.
So a very good day to everyone. My name is Manoj Khetarpal. I'm a technical support engineer for the Midas IT. And I've been working with Midas for the past 2 years. And with us is our guest, the associate director, or I should say the ex-associate director for the AECOM UK, as he's being shifted to US. So very welcome, Andrea. I hope you're having a good day.
Thank you, Manoj. Yeah, great day. Thank you. So welcome everyone. In today's webinar, we're going to be talking about integral abutment bridges, and particularly we're going to be looking at an application that I was recently involved in. The content of today's presentation should be now on your screens. We're going to have a general introduction to integral abutment bridges. We're going to look at the project, Metronet YRE, just an overview and the bridge types, and then we're going to dive into Midas Civil, and we're going to look at ways to model integral abutment bridges, and then how to take into account construction staged analysis, and then how to move into the design directly within Midas Civil. So before we start, just a little introduction of who I am. My name is Andrea Caristo. I am a complex bridges engineer at AECOM US, and previously I was an associate director at AECOM UK for 7 years in London. Beside work, I also sit on the editorial panel of the ICE Proceedings Journal of Bridge Engineering, and I am still the deputy treasurer for the YABSE British group, but I am due to step down very soon due to my move to the US. Okay, let's get started. So first thing first, what are integral abutment bridges? Full integral abutment bridges are a type of bridge where the superstructure and the substructure are rigidly connected together. What happens then is that they move together and they accommodate the movement through rotation and translation of the foundation. This means that forces are transferred between the superstructure, the deck, and the substructure, our abutment piles, and so on. This also creates complexities in terms of an interaction between the soil and the structure, which is referred to as soil structure interaction. Integral abutment bridges are more difficult to design than regular bridges. However, they've proven to allow for overall lower depths, saves in material and therefore CO2 associated with the design, enhanced structural redundancy because the structure is inherently redundant. There is no simply supported spans. Improved seismic response as a consequence of this. Lower overall construction cost and maintenance, particularly over the long term because we don't have bearings and movement joints anymore. This makes integral abutment bridges particularly attractive. And as of about 10 years ago, we have about 10,000 full integral abutment bridges just in the United States. When we look at bridge types for fully integral abutment bridges, we find a lot of differences around. I took this picture from a recent paper from Dr. Mitulis from the University of Birmingham. And we can see here that integral abutment bridges can be funded on frame abutment, full height retaining walls, really. Embedded wall abutments. We can have bank pad abutments, and we can also have what's referred to as flexible supports, so integral abutment bridges on piles. These are not the only type of integral abutment bridges. You can come across another type of integral abutment bridge, which is called the semi-integral abutment bridge. In this case, the difference is that effectively the superstructure will not have movement joints, but movements at the supports is taken care of through the use of movement bearings. So the superstructure, the back wall, and the approach slab will move together, and they will move over bearings. There are still no expansion joints in this type of bridge. And I've left there, if you want to look more, there is a report from the New York DOT that you can dive in and will give you better background on same integral abutment bridges. Today's talk will look at fully integral abutment bridges because this is what was used in the project example. Okay, so
Uh,
yes.
yeah, and I wanted to know what would be the limitations we have when we are using the integral
Yes.
abutment bridges here.
So limitation in integral abutment bridges will depend on the type of structure and subsoil, really, the substructure. So what happens with integral abutment bridges is that, as I said before, movements are accommodated by translation and rotation of the substructure together with the superstructure. And so under thermal cyclic loads, there is a push and relief effect in the soil behind the abutment walls. So a typical abutment wall will experience a hydrostatic pressure like what you can see here on the screen. This is the at-rest pressure effectively. And as we have an expansion and contraction cycle or a contraction and expansion cycle, the abutment and the deck will move towards and away from the soil. And this is repeated over the life cycle of the structure. So the design time now is 120 years in many countries. So we will have seasonal changes in temperature and seasonal movements. This cyclic load
Okay.
actually gives rise to a different distribution of pressure, which if you carry out a full soil structure interaction, for example, in Midas GTS NX, you will find a distribution of forces behind the abutment that looks something like what you see here on the screen. So
Yep.
we have a significant change in shape of the pressure behind the abutment and a significant increase as well. When we look at from K0, we can see that the peak can be 5-6 times more. This type of effect, this time-dependent effect due to thermal loads, is called ratcheting effect. And this really limits the maximum span that we can find in integral abutment bridges to date. If you ask me how long we can go, it's very difficult to find actually a maximum, and agencies around the world are still debating what the maximum limit is. So I've done a little research, and what I found is that in the UK, the former highway agency, formerly called highway agency, let's say just the highway agency, Highways England, uh, asks designers to consider integral abutment bridges as the first solution for any bridge up to 60 meter in span, and I should say 30 degrees in skew. However, similar recommendations from the Quebec Department of Transport actually ask designer to look at integral abutment bridges up to 150 meters. And then if we move to the US, this varies by DOT, Department of Transport. As far as I'm aware, the longest integral abutment bridge in the US to date is the Happy Hollow Creek down in Tennessee. And the span is almost 1,200 feet, so 358 meters. And this is, however, not the longest integral abutment bridge that I've come across. And as far as I'm aware, the longest one in the world is currently in Italy, just outside Verona, and it's called Isola della Scala Bridge. And the span is just above 1,300 feet. You can see there on the screen, 400 meters.
Yeah. Yeah.
The maximum length in reality is heavily influenced by the combination of the geotechnical conditions on site and the substructure selected. There is an interesting, paper on integral abutment bridges that was presented at a YABSE conference in 2018 by Zordan, Brisigella, and Lunn. And what the authors did is they took the Isola della Scala design and parametrically changed the span to see what would be the maximum span that bridge with that particular geotechnical condition could reach. And they found that the span could be pushed by another 140 meters to almost 500, well, to 540 meters, so almost 1,800 feet of span, which is considerably more than what the current UK guidelines are asking designers to do. So we might see an update in this space, and we might see that longer and longer integral abutment bridges will be requested by agencies around the world. Okay, this is a brief introduction on the integral abutment bridges. I'm going to move on now to the project, and I'm going to present to you what we will be discussing today.
Yeah. Before you move in, I would
Yes.
like to ask a bit about
Absolutely.
ratcheting effect. So you asked about, you told about the variation of the cycles, right? About the cyclic loading. So this is due to
Yeah.
the seasonal variation you are talking about, right?
Yes, so there's actually a recent paper that looked at day variations and seasonal variations
Okay.
over the lifetime, and it is the paper that I presented before with the ratcheting effect. Um, Effectively, I spoke about contraction, expansion, and expansion, contraction, and there is a recent paper from 2018 that looked at that. And although there is an initial difference response for the first 5 to 10 cycles, let's say, uh, depending on whether the bridge is connected to the substructure and then it first undergoes an expansion and contraction cycle or a contraction and expansion cycle. Over 120 years of life, that paper proved that there is virtually no difference to the bridge. So the thermal cycle that I was talking about are seasonal thermal cycles. So
Okay.
we go. This is what ultimately, the difference in temperature. So maximum difference in temperature that the bridge will experience over seasonal cycles.
Okay.
That's what ultimately over the long term will determine the maximum pressure that the bridge will experience. Yeah.
Okay. Okay.
Okay, moving on to the project then. The project we're going to be presenting today, it's called Metronet Yanchep Rail Extension, WIRE shortened. This project is in Australia, Western Australia, in Perth. And the project aims is to expand north of Perth, the current light rail network called Metronet there. The particular part I was involved in is regarding bridges. Integral abutment bridges, as you can guess. I was the technical lead for the design of a number of crossing over the rail that carry either vehicular roads, so roads, or interestingly fauna loads, so crossings for animal. There is a total of 13 structures that I've been involved in as technical lead. You can see them circled on the screen there. And effectively, this structure can be grouped into two different groups based on the construction technology used. So we have, as I said, two types of bridges. Type 1 is what we can call a bottom-up bridge. This is a bridge on full height abutments, as you can see here. We have our full height abutment here, backfill of the soil. We have an integral connection here, approach slab resting on a little corbel in the wall. And the superstructure is made of precast beams. These are typical beams in Australia called T-ROF. They're standard beams. In this case, they were actually taken, they were bespoke beams of the standard beam. And the name bottom-up bridge comes from the construction stage, the construction sequence that you will see on site. So effectively, for this type of bridges, the foundations are built, then the beams are erected onto the foundation, a simply supported beam. Then the slab is cast, and the end node, the end diaphragm is cast, so the bridge becomes integral. Then the operations for backfilling are completed, and then the bridge is furnished in terms of wearing surfaces and barriers and so on. So this type of bridge, because it goes from the bottom upwards, it's called bottom up. The other type of bridge is what we call a top-down bridge. In this case, the bridges are funded on piles. These are embedded piles. The deck for this type of bridges was a voided slab, post-tensioned in situ. And the typical construction sequence for these bridges will go through the construction of the abutments, then the construction of the deck and post-tensioning on temporary supports. If we then go and cast the end diaphragm so that the structure becomes integral, we furnish the bridge, and then we start excavating the bridge. So top down, because we start the construction from the top, we finish the deck, and then we start excavating underneath the deck. So this is the difference between the two names.
And any other reason for taking a separate superstructure type here, or like a voided slab?
So you're asking what drives the decision of using one or the other, basically. In this particular project, the decision was driven by the contractor. Actually, this was a design and build, and they were on a tight program. And for some bridges, they needed to have they needed to start building the foundation, the substructure, let's say, and have a free corridor where to move materials to the next site. And for those bridges, then the bottom up was the ideal part. While for those parts of the site where they didn't need to basically build a railway line before finishing the bridge, for example, or managing passage of materials, so they could wait for the excavation to happen at the end of the bridge construction, the top-down bridge was selected. So it was driven by this, and obviously it could also be driven by the geotechnical condition of the site. In this case, it was driven mainly by construction program, really. Yeah. Okay, so this is just a brief introduction of what the project looked like. Let's now dive into Midas Civil, and let's look at how you're given this bridge. How do you start modeling? What functions I find are useful, and what are the features that I really like in Civil to do this type of structures? Let's start with the model definition, the geometry. You will all have used Midas Civil. Midas Civil allows you to define the geometry of a model in many different ways. I've listed here the graphic user interface. We can click on the interface and define nodes and elements. We can also define everything through MCT codes. We can draw everything up in a CAD software and import it as a DXF. Or usefully, we can use the wizards. And I particularly like the grillage wizard, and this is what was used in this project. And effectively, the grillage wizard can be accessed through the menu, the structure menu. You will find something called grillage model. You can see it here on my screen now. And what that opens up is a very easy to follow step-by-step definition of your bridge. We have here some tabs that look at the layout of the bridge in terms of general layout, span information, for example, 3 span at 40 meters long each. We define here the materials. Then we move on to the definition of the span and the cross section of the span. Then we look at transversely how the loads are distributed. Then we define all of the loads, the tendon, and the reinforcement. In this presentation today, I'm not going to dive into the details of this because there is already a very good presentation that Midas provides, and I put here the link for you to follow. So if you've not used before, this is a very powerful way to define your grillage models in Midas, and I highly recommend that you look at this tutorial. Once you finish using the grillage wizard tutorial, what you find yourself with is something like this. This is a 2D grillage, and you have all of your beams defined, your transverse elements are defined, and the basic composite sections are already defined, as well as the basic load groups. And if you're conversant with Ashto, you will find that the load grouping name is actually very easy to follow. You have DC, DW, DC1, DC2, and so on. For this project, however, we did not stop at using a 2D grillage, but we moved to towards 3D spatial frames. And what I mean by that is that the integral abutment bridge, we spoke about soil structure interaction and how it's fixed with the substructure, and the flexibility of the substructure is really important to correctly represent the effects of the deck. So one step forward from the grillage wizard is to create the substructure. And to obtain the final geometry, I find that the extrude function in Midas is really easy to use and really powerful, and allows me to create the model, the geometry of the model, very quickly. If you're not familiar with the extrude function, you can find it under node elements. It's this icon here, extrude. It will pop up in your tree menu on the left, this little window. And what you can see here is that you can select the type of extrude. So in this case, I wanted to define for the bottom-up bridges plate elements to represent my walls. So these are 2D elements. They're not beam element, one-dimensional elements. They're 2D elements. And so what I did is I extruded a line element, which is the end diaphragm of my deck, into a planar element. You select the element type, which is a plate. You select the material, the thickness, which you have to have defined before through the property menu. And then you can very easily select where you want this extrude to end. And so you do an extrude downwards to define the wall, and then you can do 2 extrudes either way to define effectively the footing. So the geometry is now really defined, and that is done mainly through wizard and extruding, really. So really easy to use. Let's now look at the boundary effect and the loads. I've discussed with you before the need to account for soil structure interaction, and the need to account for that K star, let's call it that, the ratcheting effect. So I'm going to show you now how that was done. Okay, so the boundary definition and the ratcheting effects. You could go all the way and do a full soil structure interaction with GTS NX and get a similar graph to what I showed you before.
Yeah.
But there are actually codified ways of defining that maximum pressure, and these are based on limit equilibrium. Particularly for this project, although this project was in Australia, the specification required that the ratcheting effects for the full height abutments were accounted for using the methods outlined in PD 6694 part 1. This is a published document from the US, and it's a recommendation for the design of structures subject to traffic loading. And you can say it's an addendum to the Eurocode. It's not part of the Eurocode, but it explains how to apply the Eurocodes, basically. And what the code has for this type of for the bottom-up bridges, let's say the ones the bottom-up on Metronet, so the ones with the full height abutment on spread footing, it's basically a limit equilibrium method that allows us to define the ratcheting effect, the maximum ratcheting effect KD, by considering the soil property, the height of the abutment, and effectively the idea of the code is that the bridge is set in a mean position. it will undergo seasonal temperature changes. So it's going to move the maximum movement called DD in the code, which undergoes maximum expansion and contraction. And as it undergoes this cycle, the maximum and minimum pressures will over towards K star, which is the ratcheting pressure, and K0 max here. And there is one part of the code that I want to highlight for you, because I've seen people just defining this pressure here, K star, and thinking that's all I need to design for. We need to be really careful when we design integral abutment bridges, because in some circumstances, and we'll touch on them later on, minimum earth pressures may actually give you the most unfavorable load for parts of the deck or for parts of your walls. So we need to look at both the maximum pressure that we get, the ratcheting effect, but we also need to look at the minimum effects and what happens during contraction, particularly coupled with early cycles and creep and shrinkage effects. And we'll talk about it later. In terms of the definition that PD allows us to do, this is taken from PD. This is figure 5. Effectively, PD, this code, allows us to define a simplified pressure that resembles the pressure that I showed you before. If we look at what I showed before, this is what you would find from a full soil structure interaction analysis. And if we look at this, we have a triangular distribution up to this height. And then we have a trapezoidal distribution. This is the lower base, this is the maximum base, and this is a triangle. So the code basically allows us to define a pressure like this, a top part triangle, bottom part trapezoidal pressure. And the peak pressure, K star, is found through that formula that I showed you before. And this is particularly useful for us when we use civil, because civil, when you use shell elements, plate elements, like I showed you before, it's actually really easy to define this linear pressure on a plate element. And this is done through the function hydrostatic pressure load. So we can define a load case called K star, like I did here. And the loads are defined as linear loads. And these are defined on plate elements. The local direction of the plate, Z, will be the in or out from the plate, so top, bottom. The minus or plus will depend on your local axis on the plate. So look at them and you will realize whether you have to put it as plus Z or minus Z. And in terms of this, so this will give you the sign of your pressure load. The gradient goes in global Z. What it means is that global Z minus, sorry. What it means is that I'm starting from the top of the wall and I'm going down in my case, because Z is pointing upward. This is in Midas Civil, just a reminder, lowercase is a local axis, uppercase is the global axis of the model, okay? And what all we need to define really to do that, trapezoidal triangular shape is define the reference level at which we are starting our line, define the gradient intensity, and define the constant intensity. The gradient intensity is effectively the slope of our line, and the constant intensity is the hook point of our line. What I mean by that is that we can define, for example, this triangular part here. Very easy. We start at 0, we go down with a certain slope, we don't have any intensity. When we catch here, what we have is we already have a certain intensity. It's this one, gamma times h divided by 2 times k star. And then we need to lower it to gamma times h times k0. And we do that by anchoring here the intensity using a negative gradient, let's say, so that our slope is either positive or negative, depending on how your axes were before. And the reference level in this case will be the midpoint here, the h over 2. Okay, so it's really easy to define this type of pressure and calculate it as well by just following the code. However, unfortunately, when you have flexible substructures like pile, the limit equilibrium method do not actually allow us to predict correctly the pressure from ratcheting. PD 6694, apologies, part 1, as a part of the annex that allows us to define these pressures. We do need to do a soil structure interaction analysis, so we will need to run a pile, a model of the pile under thermal cycles with correct axial and torsional restraints at the top to model the deck, or we can model the entire deck. And effectively, what we need to define in this case from the model is the maximum expansion, DD, the one that we spoke about before. And then what we need to identify is basically two different dimensions, let's say, according to the PD 6694 Annex 1 guidance. The first dimension is this H mark. H mark is the depth of the soil at the abutment, where after repeated expansion and contraction, we will experience the at-rest pressure. So it is the depth at which the ratcheting effect meets again K0. And D mark D, it's not the maximum expansion, that is DD. This is the expansion that the wall, the horizontal deflection of the abutment wall, at a depth equal to half of the H first depth. Now, when you look at this first, it's a bit confusing. There is a commentary that allows, basically in the PD, there is a commentary that kind of explain what needs to be done. I've extracted here the flow chart of what needs to be done. Effectively, we define the geometry, the material property, and the soil properties and structural property in our GTS NX model. We calculate the thermal load, T max and T min, and this allows us to determine the maximum movement. There is a formula in PD to do that. We start with an estimate of the initial soil strain parameter. These are D marked and H marked that I spoke about before. We calculate the long-term soil stiffness distribution at the H marked depth, so where we're going to have K0, and the soil passive resistance. We then run our model in GTS NX with a monolithic push, a cycle of expansion contraction. We identify H mark and D mark, and we look whether or not these are in line with what we assumed. If they're not, we have to go back, update our H and D marked parameters, recalculate the long-term stiffness distribution, and repeat this cycle. We stop when basically there is no more difference between what we previously used as H mark and D marked and the ones that we found. And this allows to basically get consistent pressure and displacement in the soil. And what we get out of it is effectively a distribution of pressure. That will be our K-star pressure. And we also get we can read the stiffness below that point. So below the point, below H mark, where our K star meets K0, we're then going to use distributed springs in our pile. And above that point, we're going to use the distributed pressure that we read from GTS NX. And we need to input that behind our pile. So it's an iterative process. Out of experience, it takes about 3 to 5 iterations. That's my personal experience on this project and other projects, but you may have different experiences. But I highly recommend that you follow the PD6694 Annex A, and particularly the commentary to PD6694 if you haven't done it before, because it's quite clear. And there is a guided example that you can follow. So,
sorry to interrupt, but
yeah, no problem.
So how does a designer decides to which reference to take? So is there any other reference we need to take, or it has to be PD6694?
Yes. So no, it doesn't have to be PD6694. In this case, it was a requirement of the client to use this, and that's probably why I was involved in the project in the first place. This project is in Australia, but they're using a published document from the UK. So I think that's the reason. In reality, there is a lot of research around integral abutment bridges, and there's actually research that comes straight out of Australia from Professor Lehan. And this research has actually found its way into Midas Civil. I don't think any other software has this as a feature. And effectively, in Midas Civil, you can define boundaries for integral abutment bridges. We did not use it on this project, but I am going to show you here how to define it. And if we go under our boundary tab, there is a little define support, and in spring support, there is actually integral bridge. And what this allows us to do is to select the type of deck that we have. We have a deck on full height abutments, bottom-up bridges, what we call bottom-up in this project, or we have a deck on piled abutment, what we called a top-down bridge. And what Midas allows us to do is effectively, after inserting the properties of the soil, the stiffness of the deck, and so on, it allows us to easily define for all our shelled element or beam elements compression only springs that will be activated only during expansion towards the soil. as well as linear elastic springs, both vertical, lateral, and torsional, so rotational springs. And the end result when you use this will look something like this. So Midas Civil will allow you to easily define, following the study of Lehan, all of the springs directly and take care of all of the stuff that I spoke about before. It's very well documented in the Midas manual, and there is also a blog post that I found really good when I tested this out. So I highly recommend these two links. I put them here for you. This is the manual. This is a blog post from Midas, official blog post, and you can follow this, and it basically saves you quite some time. Let me put it that way. Okay, so this is how we define the pressure and the boundaries for our integral abutment bridges. I am now going to move on the definition of the live loads. I'm not going to touch on the definition of the live loads in terms of how you define lanes and standard vehicles, but I want to show you something that I find very, very powerful in Midas, and that is the definition of non-standard vehicles, what Midas calls user-defined vehicles. These bridges, as I said, are road bridges. They were designed for all of the normal Australian loads. So if you're familiar with Australian code, this is S1600, M1600 loads and the various other single axle vehicles, let's say. However, Western Australia, the area is an area that has a strong mining industry, and they have a lot of non-standard heavy vehicles connected to this industry. And when you design in Western Australia, you need to take care of these vehicles. These vehicles are defined into a local code that's called the Main Road Western Australia Bridge Branch Manual, Design Information Manual. And when you design there, you need to define these loads. And these vehicles, you can see them here. They're very long vehicles, a lot of axles, and very heavy. And Midas Civil allows us to define vehicles through the load tab. We can go into moving load. We select the code. In this case, it's Australia. When we go in vehicles, you will see here that you can define standard vehicle. These are your A160 MNS 1600 that I talk about. But you can also define user-defined vehicle, add user-defined vehicles. And when you click on it, what you find is you come up with this define user-defined vehicular load. And when you go on permit truck, you can actually define very complicated vehicles with a number of axles and a number of wheels per axle. So the way the way this window works is that this part here allows you to define the transverse distribution of loads, while this part here allows you to define the longitudinal distribution of the load. What I mean by longitudinal is the direction of traffic, and transverse is in the cross section of our bridge. So what you see here on screen is a vehicle in which the 9-ton axle is made up of multiple wheels. There is at least 5. We can see here on the screen. D1 is the distance taken. You can see here. It's the distance of wheel 1 from the central axis of our vehicle. If you click on symmetric vehicle, the vehicle is made symmetric about this axis. Otherwise, you can do it differently. Evenly distributed, basically, you just define one wheel and then it will distribute it. You don't have to define anymore the weight of the wheel, the kilonewtons or kips of wheel weight. We didn't use it here, so we repeated 7.36 everywhere. But yeah, you could have done that. So this allows you to define, as I said, the axle, the transverse part, while down here, we put the longitudinal distribution, the way along the line of movement of the truck. And these are defined by selecting the type of axle and then the spacing from the axle, the preceding axle. So really easy to use, really easy feature to use. And yeah, everything that I said is very well explained in the user manual. So I left here 2 links for you. They should have appeared now on the screen.
I
Yeah.
Also, I can see the impact factor is given as 0. So you
Yes.
considered them as after in the
No.
load combination. So
Yeah, so this is due to the specification of the project. Basically, without going into too much detail of the Australian standards and the bridge manual,
okay,
there are
okay,
these vehicles need to be they have different impact factor, dynamic factor, let's say,
okay,
based on whether they're going to be supervised or unsupervised vehicles. And these vehicles were run actually without an impact factor, and then the load combinations, basically the supervised and unsupervised cases were done that way, simply because it saves running time. Because obviously, if we were to define one with 40% impact factor and one with 50%, we would then have multiple moving load cases. While since it's only that difference and the axle load and distances and all that is the same, it was quicker to run the models this way. But yes, you're right. You could define here the impact factor. That is your IM factor, the magnitude factor. So dynamic amplification factor. There is also in the moving load case where you can define factors in Midas. So, but yeah, you're very right. Yeah, it was done in post-processing.
Okay.
One thing that I really like about Midas Civil, and I have seen that other FE modelers don't have, is the possibility of using the moving load tracer. And for some reason, this is missed oftentimes by users. So I really want to bring your attention to this. Once we've run our moving load analysis, in results, there is this little drop-down menu called moving tracer. And if you click, you can select, for example, beams. And this allows you to basically quickly define the position of your very complicated truck that you just defined. And you select the key element. This is a beam element. I select a random element along the deck, and I asked Midas to give me the maximum case for a supervised GR2 vehicle 5. So this is a special vehicle running in a certain lane. And what Midas is showing me is the maximum value associated to MY. This is the effect I'm maximizing, and the distribution of load. I can see graphically how the wheel have been placed. This is based on influence lines, but this is really powerful because sometimes DOTs or clients in general ask us to report on the position of the loads, and but also report on certain design summary sheets, for example. And this is really powerful in Midas Civil because there is this function down here. So you select the key element, and there is this function here that's called write minimum maximum load to file. And what that brings up, it's actually a bunch of lines of MCT code. MCT code is the code that runs behind the scenes in Civil, let's say. Even if you don't understand what this code looks like, this is actually an extraction of what we saw on the screen now. It's a representation of this vehicle made as beam loads and point loads. These are concentrated loads, and effectively I can extract that. And if I need to create a side model or anything else, I can just define that load, and I don't have to rerun the full moving load analysis. And this is really powerful when we need to report to our clients the position of the moving load, the critical moving load. And this can be done, I showed it to you for moments, but it can be done for plates, for moments in beams, sorry, it can be done for displacement in plates and beams, maximizing effects on elastic links or bearings or reaction effects. So it's really, really, really powerful tool. Another thing I want to bring your attention to is sometimes moving loads analysis can take a lot of time, and there is a little function in Midas. It's under the analysis tab. You click on moving load, and this window, the control data for moving load, will pop up. Not all possible analysis methods are available for each design code. So when you define the load, you choose Australian code, AASHTO, Eurocode, Canadian codes, whatever. You have different analysis method. The standard analysis method up until, I'm not going to throw the number there, but up until a couple of years ago, basically, only the exact method was used. Now, for some codes, you have the pivot and the quick. But here, effectively, you can select what type of results you want to take for plate element, center or center plus nodal. Do you want to register stress, concurrent forces? Do you want to register concurrent forces for your elastic and general links? But particularly the calculation filter can save a lot of hours of your run. What I have selected here is reaction, displacement, force moments, and elastic link, and all. This run is going to calculate results for every single point node on our model. However, if I know that I'm only interested in getting the results for my main girders, I could define a group called main girder. This is a structural group. We'll talk about groups later in the presentation, but effectively I can select group, drop down menu, select my group, and moving load analysis will only run for those elements that I selected. And this can really save a lot of time in a run. So I highly recommend you play with this when you have a really big model on a lot of loads, because it can really save time for you if you know that you don't need all of the output for every single element and node in your structure. Yeah. Okay. So this was an overview of some of the functions that I find really useful in Civil. But we spoke about integral abutment bridges, and we divided into bottom up and top down about around their construction sequence. So the next topic is actually the construction sequence in Midas, and I want to show to you how you model the construction staged analysis in Midas. And to start, I just want to define the very basics of construction staged analysis. So the construction staged analysis in Midas is accessed through the load tab. You click on construction stage, and then there is this define CS here, and this opens up this pop-up menu, construction stage. Now, construction stage is central to Midas, and it's one of the really to Midas Civil, sorry, and it's one of the strength of the software really, and much easier to access it through here. There is always a little icon here that you find there, and you can just access the same menu there, which is what I normally do. The construction staged analysis is based on the possibility of mimicking basically the time, um, how our bridge is going to be built on site, accounting for time dependent materials as well. What I mean by time dependent material is the possibility of modeling in our bridges the evolution of the compressive strength of concrete as concrete ages, as well as the development of shrinkage and creep effects in the concrete, which in pre-stressed concrete analysis will also lead to the development of losses from our initial tendon force. So I'm not going to touch on the definition of the time-dependent materials, but you can find really good tutorials on the official Midas YouTube channel and on the blog post that look into the details of how to define this. And just for clarity, these are defined into properties. When you define your material, there will be time-dependent materials, and then you have to create you have to define a time-dependent material for creep and shrinkage, one for compressive strength development in concrete, and then there is a material link. So you can see them here under your material. You will have these parts here, and these will be linked directly to what you see here, the duration. So the time when the element is activated, that's day 0, or you can define differently. We'll see it now. And then it just uses the duration to count for the time-dependent effect. Before we look into details at the construction stage definition, though, I just want to touch on the basic concept behind the construction stage analysis in Midas. And this is the concept of grouping. In your tree menu, when you work, you mostly will be into works, probably most of your time, but there is a part of the tree menu called group. And when you open it, you see that there are 4 basic parts: a structure group, boundary group, load group, and tendon group. So these are, I'm just going to show you what they mean, what they really represent. A structure group is a group of elements or nodes, okay? So we right click on structure group, new, we define a group, and the group, when it's created, will have 0 node and 0 elements. We drag and drop on the screen or through the selection little selection box. We can select the elements that we want, the nodes that we want, and it's very easy to drag and drop, for example, the name of the group with your selection there, or you can right click and do add to group, assign from scratch, so clean the group, or just add to whatever is in there. Structures group basically refer to elements and nodes. There is another type of group, which is the boundary group. In this group, you will put your supports, your links, your stiffness modifiers, for example. So if you take a boundary group, you select some nodes and you drag and drop this boundary group onto the window, this little pop-up comes up, and you can see here, I think this is really clear because here it tells you exactly what type of boundaries you can assign to a boundary group. And you will need to assign this if you're using, for example, a width scale factor and you're using a construction staged analysis. You need to activate that in the construction staged analysis, and we'll see how to do that later. But you need to understand that everything that you put as a support, a link, and so on needs to be assigned to a group. If it's not assigned to a group, your construction staged analysis will not know when you need to activate it, and so it won't work. Moving on to the other group, this is the load group. This is not a group that you see on screen like the other ones. It's not based on nodes or element, but actually to access it, you go onto your load case, you right click onto your definition of loads. In this case, I went for nodal loads. There is this tables here. And when you open the table, you can see here the group. Now, when you define a load, there is a load case definition, and underneath there is a group definition, which starts as a default. If you don't define the group, it will be put on default group. Um, Again, in a construction staged analysis, you need to have defined groups for your loads, and these groups are activated at the stage. So you need to be sure that you've grouped your loads correctly based on activation, and otherwise you cannot use them really. But it's really simple to do, and it's really easy to check through the tables which load is associated to which node or which element, and which group this is assigned to. And then in the construction stage tree, you can see when it's activated and deactivated. Last group, it's the tendon group. This is not a group that again you see on screen, but it's a group that is defined when you define a tendon property. There are very good tutorials to define tendons in Midas. There is a whole world to define tendons behind Midas. I personally like to use the MCT, but you can use the graphic definition here. But effectively, the tendon group is assigned up here, and you need to define a group for your tendons when you use the construction stage analysis and the design. And if your tendons have different properties, you will want to define different tendon groups. So this is a tendon with 25 strands in it. This is the typical tendon. This was a trial tendon, so I had to create 2 groups. But yeah, it's again, if you don't know these things and you try to do something and you didn't assign the 2 tendon groups, might as well give you an error saying you need to assign different tendon groups. So it's really easy to follow. Okay.
So
Yes.
how do you fix the shape of the tendons? Like how a designer fix?
Sure. So the shape of the tendon in Midas, as I said, you can do it in multiple ways. What we've used in this project, you can see here, this is a tendon that's assigned to element 226 to
No, no, no.
251.
I meant how a designer fix the the shape of the
Oh,
tendon.
the profile of the
Yeah,
tendon.
yeah,
Yes.
profile
Well,
of the tendon. Yeah.
okay. This is a very good question. Yeah. So this really depends on a lot of things, actually. So in this project, we have prefabricated beams, and we also have cast in situ deck with post-tension tendons. Now, the idea behind pre-stressed concrete is, in very simplistic terms, is to basically, we all know that concrete is really good in compression, not so good in tension, and of course we have reinforcement taking care of the tensile part. But the idea behind pre-stressed concrete is really to enhance the bearing capabilities of our elements by assigning let's call it artificial pre-stress, an external force through a specific element that's our tendon. It's a high grade steel tendon, which is stressed, tensioned, and then locked in place and released, and it basically introduces a compression, into our beam. What that allows us to do is effectively get rid of areas where we have tensile stresses, or at least reduce them, right? The way you want to do it is basically follow the development of your tensile stresses. So for a casting, for a simply supported beam, we have a sagging moment. So we will have tension at the bottom fiber. We want to basically contrast that tension, and so we want to give it a compression at that fiber. So the optimal solution in that case would be a draped tendon with a parabolic shape that follows the eccentricity. So it goes from 0 eccentricity as a support, if it's simply supported, towards a maximum eccentricity. Now, you cannot just follow always the bending moment diagram, because sometimes actually, particularly with prefabricated beams, there are costs associated with fabricating the beam, right? And so sometimes the precast yard don't have the possibility of placing the tendons in your strands, monostrand, let's say, in the optimal way. Or it might be that they don't have the end block that they're limited as to the areas where you can place it. So for pre-tension beams, I highly recommend that you talk to your prefabricator, really. and agree with them at the start of the project how to place your tendons. But for this project, just to finish, the prefabricated beams all had straight tendons because it makes the fabrication of
Okay.
beams very easy. It's not the optimal way, maybe,
Mm-hmm.
not for every load case, but it was when you look at the balance of constructability, cost
Yeah.
of
Yeah.
creating the
Yeah.
beams and everything, it was the best solution.
Okay.
While for the post-tension decks, we have a parabolic tendon distribution, like I discussed before. Okay, moving on to the construction stage. Now that we spoke of groups and we have an understanding of them, the construction stage analysis is based on this little construction stage menu that I showed you before. And then when you click on add or modify the existing construction stage, this compose construction stage menu pops up. You have it here. Here we define the name of the construction stage, the duration of the construction stage, and then here we have tabs, element, boundary, and load. These are the groups that we defined before, right? And the idea is that literally you activate and deactivate elements, boundaries, or loads as you need. You define here the duration, as I said. Here you can save the results for stages. If you want to add additional steps, use this part up here. You can define a number of steps between 0 days and whatever duration you have, and you can save the results. This is particularly useful for pre-stressed concrete, for example, if you want to look at transfer. Okay, so this is how you define the stage. Now let's look at the bridges for Metronet YRE. Let's look at top-down bridges. The first step is the installation of pile and casting of the capping beam. And so this is what we need to activate in our construction stages. So we activate all the pile group and the capping beam. And there is no loads other than self-weight at the moment because we have not excavated yet on site, right? So these are drilled in place piles. The second stage is the definition, this the casting, of the deck. And what we need to do is cast deck on temporary support. What the stage will look like is this. These are springs applied to the piles. As we activated the pile, we also activated some springs. And this here are compression-only springs that represent the temporary support. On site, what they will do is they will excavate a tiny bit, put here false work. That false work has a certain stiffness, and then they will cast wet concrete really on it. And what we need to define in Midas is we have this boundary definition here. Sorry, you see it here. It's a surface spring. And we can define surface spring from frame element. And what we can do is basically we define a certain modulus of subgrade reaction. This is the stiffness of our temporary false work plus soil group. And we use frame elements because our beams are frame elements. And we define an effective width, so the width associated to each beam. In this case, the beams were equidistant on both sides, so this is the distance between the center point of each beam. The type of spring is a compression-only spring. The direction will be the direction that compresses under self-weight. And this is how you define very quickly all of these springs. And the definition of these springs here, so this is for frame, and this, as I said, is the compression only. And the definition of the springs allows us to have this stage here. Now we have compressive springs for all around the deck. The next step is the installation of tendons and stressing of the tendons, right? This is done once the wet concrete that we just activated, which is now lying on our compressive only springs, has reached 40 megapascal. This happens after about 10 days for the type of concrete we were using. So after 10 days, we activate the tendons through the tendons load and we stress them. This is done into the load tab of our construction stage compose construction stage menu. You see here we activate tendons. We have reached the 10 days maturity. So this is done on the first day of this special load step that's called post-tensioning, which has 1 day of duration. And what we have here is these tendons are activated and they're stressed on elements which have a stiffness of 10 days associated to them through the to the time-dependent compressive strength material. What happens then at the end of this stage is that we have the undeformed beam, which was basically not moving on our temporary work, and the deformed beam after tensioning. We can see very well in civil the uplifting of our beam. It's uplifting all the way. So it's what this means is that the temporary supports are no more engaged, and so later on during construction they can be removed effectively. And so our deck is now effectively acting as a simply supported beam pre-stressed. We then have to cast the stitch joint, the end node, and what this makes is it makes our deck and our substructure connected. Okay, so at the moment the deck is acting as a simply supported beam. It's pointing upwards after our post tensioning. We're casting this end node, and the end node is represented by a boundary. We've decided to basically model it as a boundary element. This is a rigid elastic link. We used elastic link rigid type and not rigid links master slave nodes because we can read the forces inside of these elements in Midas Civil. And to do that, what you do is you go into your boundary tab in the construction stage menu. And there you go. Here we activate stitch, and there were some beam end release at the end of the beams in order to avoid picking up any moment towards the ends. And these are deactivated. So this is how you really do it. Yeah, you can see it here. Okay, now the bridge is basically almost finished. You can see here we have our beams, they're post-tensioned, we have our piles, blah, 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 and we also have our elastic links. It's time to then apply SDL, superimpose that load, and let long-term creep run. The SDL loads are defined here. They're grouped as SDL and they're activated in a certain group. And to actually model the long-term creep effect, all we have to do, as I said, is let the days run in our construction analysis. So what I defined here is a construction stage which has a duration of 10,000 days, and associated to the other ones allows me to get to my target date for long-term creep definition. So we went from this piles and beams to this fully fledged deck with post tensioning, and we've taken care of all of the stages. So we've taken care of applying the loads as they will be applied on site. Another part that I want to take your attention on is the possibility of defining composite beams. If we look at the bottom-up bridges, we have precast beams that come to site, and then the slab, once they come to site, they're taken off the truck, they're put onto the deck, and then onto the abutments, apologies, and then the slab is cast in situ, and then the stitch is cast. These beams are defined as composite beams, and in the composite, in your construction stage, you will have to use this function, composite section for CS. You see here, again, since this is basic to Midas Civil usage, you can access it here, same thing. And this is really easy to use. It's really simple. This is the menu that you will find. What you define, first thing is you define the activation stage of the beam element. This is the beam when it comes from the truck and it's loaded onto the abutments, okay? The section type, in my case, in this model was section number 31. Eglinton was the name of the bridge, and this is the width of one beam. The composite type is normal. And then here, down here, this is where the magic happens. Part one of the beam is the activation stage. This is when you define a composite beam in Midas, you have a part one and a part two. Part one is the beam itself. Part two is the slab in this case, okay? Part one is material S50. This is a concrete in the Australian code. It's activated at the active stage that I defined up here, stage one. Its age is 10 days. So it has some stiffness because our stiffness, remember, if you put 0 days, there is almost zero stiffness to your concrete because we're doing a time-dependent material. And then the second part, this is our slab, is cast at the second stage. It's called stage 2. We're casting it with a bit of stiffness. This is the day where the formwork basically will be removed. So 5 days after the wet concrete. So there will be a stage where we have the beams with the wet concrete load. And then there is this stage 2 where the concrete is hardened. And this is how it's activated. So it's really simple to follow. Last thing I want to show you on the construction analysis is the construction analysis control, because there is a very important little bit here. I activated those SDL loads, and I showed you before how to activate them. That was the group. But I also want to look at the effects of SDL loads during construction stage alone. This is important because SDL loads, in almost every code that I'm aware of, they might have different combination factors based on whether they're being looked at, for example, early days, long days, whether they are a long-term initial wearing surface or long-term wearing surface and so on. To do that, Midas Civil gives us the possibility of defining erection loads. You see them defined here. If we click here on add, this window pops up. Here you can define the name, define the type of construction load that it is for the construction staged analysis. And here you have your load case. And in this case, I put in SDL all of these loads. So why is this important? This is important because once you do that, in your output of your construction stage analysis, you will have the erection load case as the LCS. This is really important because you want to carry in your load combinations the loads as they happened in the construction stage analysis. So bear this in mind, and I'll show you why this is important. So naturally, we now move to the load combinations, which will allow us to then move to the design. Load combination in Civil are under result, so they're in the post-processing part of the software. There is a self-explanatory little icon called load combination under combination. And this is what the menu looks like in your combination. There is a tab at the top. When you open it, you will be on general. If you decide to use the design features of Civil, which in my opinion are really good, you will have to define your load combination either in steel design, concrete design, composite steel girder design, based on the material that you're designing through Civil. The load combinations in Civil are really simple to define. They effectively, you define a name, you define the type. Strength is a ultimate limit state type of combination. There is also service that will be used, for example, for serviceability check, for example, displacements and so on. Add the type means that you're adding all of the single load cases here. If you do envelope, it will create an envelope of the load cases that you select here. You select the load cases here and you select the factor. These are the combination factors, okay?
This looks like a very big list. I can
It
see the
was a
number is
very
going
big
till
list. Yes,
235.
exactly. Yeah. It is a very big list. And actually, you don't have to do it manually. What I showed you now is you do manually. But actually, if you can do it very very flexibly through using the spreadsheet form. I don't have really slides to show you how you do it, but effectively it will look like a spreadsheet on Excel. It's a very easy to follow table, and what you can do is you can define a lot of combinations beforehand and then just call them up through the spreadsheet, and that's how you can do it. You can also from that spreadsheet then create a very simple MCT code and load them in through an MCT. Nobody has time to do 220, 230, and they keep going. You can see that there is probably another 100 or something down here. But one thing I want your attention on, you see this tendon secondary as a CS there, okay? Normal static load cases, apologies, will have ST on it. I want to just spend 2 minutes on it because it's really important that you understand the difference between these because it can bring really big problems. So the importance of the construction staged analysis is cannot be underestimated. Our bridges are, for the bottom-up bridges, we looked at it before very briefly, but what we have is the bottom part of the bridge, the substructure is built. Then the walls are backfilled almost to the top. Okay, you can see it here. Then the deck is brought into place. This was driven by construction timelines. And effectively, the contractor wanted to have complete disjointed erection of the deck from the erection of the substructure. So this is what we gave them because that's the need of the contractor. Now, if we look at the dead load, we spoke about it. These beams are coming to site. They're being lifted off the truck, put down onto the abutment. They act as simply supported beam. So what you expect is that the bending moment diagram is a simply supported beam. QL squared over 8, W squared over 8, right? So it needs to be fully sagging. No, nothing at the top, nothing at the supports, right? We don't have to have any moment at the support because it's a simply supported beam. This is what we see in the dead load output for the construction staged analysis, CS. However, if we're not careful and we use the self-weight load case, ST, this is the output that we get. Okay, there is a lot of hogging you can see here because the beam is basically flashed onto a frame structure. Now, the CS load cases are applied to the active structure with the active boundaries at the stage where you're activating that load, okay? This means that if the beam is a simply supported beam, there is only vertical support here and there is no moment passage, it will record the right moment, the what you expect. This is the dead load associated to the beams alone, okay? However, if in our load combination we start using ST load cases, we're in for troubles because we're going to have this is the correct solution for a frame structure. This is a QL squared over 12, QL squared over 24. However, when we design these beams, we need to be very careful because this maximum sagging moment is a lot lower than this. It's actually a third of this one. So we need to be careful because the beams in the ST load are applied to the post CS structure, the fully connected structure, let's say, and the beams will be treated as fully fixed, okay? Why is this important? It's also important for the design of the end node. And this is something I want to bring your attention to. The end node is the thing that we called stitch before. This is a very, very, very difficult part to design. It's going to be a part on site that's going to be difficult to build because there's going to be a lot of reinforcement coming from the deck into the abutment. As we say, the integral abutment bridges, they have a connection between the superstructure and the substructure. That connection cannot just be something on civil. That connection needs to be replicated on site. What it means is that we need to have a passage of moment from the deck down onto the superstructure. And to do that, we need to have continuity of reinforcement bending down into the superstructure. I found this paper from Klein very useful to follow. It's really easy to follow. You find it on Google Scholar, for example. And again, civil is great to do structural models using anti basically methods. We have a truss elements here. These are truss elements. We have our loads coming from the moving tracer, for example. And we know what the loads at the ends of the deck are, and we created a simple strut and tie model following this paper, and that's how you do the design of the end node. This is what I mean by end node is the part where the superstructure connects into the substructure. Okay, this is the deck here, and this is the wall down here, and it's this node. This is a discontinuity region, right? So you can't use beam theory to study it. So that's why we use strut and tie. Okay, perfect. Let's move on to the final part of the presentation for civil, which is the design. The design of pre-stressed concrete in civil is done through the PSC module. You select your design codes and your parameters. In this case, we're in Australia, so this is the design code for Australian concrete. And one thing that you can define in the parameter is something that not every country will allow you to do, but Australia does. These are what in Eurocode would be called a class 3 beam. So these are beams that are allowed to go beyond the maximum tensile stress in the concrete and have an increase in the reinforcing steel in terms of maximum tensile stress. And to define that, you have to go into parameters. In case you're designing in Australia, you're wondering where this is where it is. Okay, so we define our parameters, then we define our materials. This is done, here, PSC design material. This pops up. You can define the material, the concrete quality, the reinforcement grade, let's say. Then we define our output position. These are the beams and the nodes where you want to carry out the design and print out the design. Then we click on perform design. This does all of the checks. And we can look at the results from the tables, okay? PSC result tables, check flexure strength, and these are tables. And M star over phi mu, this is the utilization of your beam, okay? So we can see that the maximum utilization is about 79.92, so 79.92% utilized. This is a ULS sagging moment, and this is the load case. This is a strength 1 load case, let's say. Another part here that I highlighted before is the Excel report. You can print really good Excel reports, and these are really easy to follow. So if you're scared that civil is a bit of a black box and you're like, oh my god, I don't know what it's doing, how do I ensure that it's right? Well, actually, if you do the Excel report, you will have a very, very, very thorough report, which I personally checked line by line with the ES5100, and I was very happy with the output, so I've used it. And I highly recommend that you test it yourself, check it. Let me know if you disagree with my statement, but I thought it was really good. And basically it prints out for you, for example, which one is the load combination that is critical, what type of load combination you're looking at, what's the maximum factor moment for that load combination? This is a flexural design. It will do shear design, it will do crack check, transfer check, and everything. And you have the equations actually plotted out here. And the tables, this table here, there are a couple of tables before, and then this table here, allow you to have all of the data that goes into these formula. So you can actually check line by line this, and you will get the same results. So highly recommended PSC module in civil. It's really good. Yeah.
This is design is only taking care of the pre-stressing, right? There is no additional reinforcement that you have added.
So the additional reinforcement was actually defined.
Okay.
It was defined in the section. It's done through. Sorry, I haven't shown it, but if you go into properties when you define your beam, you can define reinforcement for each section. You have to define that to do the shear checks and all of these checks. Particularly in the transfer check and sorry, not the transfer check, the SLS check for cracking, where we allow the concrete to go beyond the maximum tensile resistance, and we allow for the normal reinforcement to pick up an extra 200 MPa in this project. You need to define that there. So yes, it's there. As you can imagine, the governing usually is at transfer. It will be the tensile, the tensile stress in your beams. Maximum compressive stresses as well. You don't want to exceed those. You have flexural checks. And obviously cracking checks. This is what normally drives your design in these beams. Okay, last slide from me. This is the product of the bridges. They're still being built, almost finished as far as I'm aware now. This is the beam being lifted off and put into place. These are the simply supported beam. We looked at the beautiful sagging diagram before. These are the piles when our piled abutment when excavation is starting, and these are the up here you have the process of casting the slab. So all of these steps are actually modeled in civil through the construction staged analysis menu. So this is it from me. Feel free to reach out if you wish to discuss anything further. You have my contacts here, and yeah, thank you for joining us today. I hope this was helpful.
Thanks a lot, Andrea, and thank you for this amazing presentation. I'm sure the users and the viewers must have gained a lot of knowledge, and you actually took us towards the whole journey of the project. And in that slide at the end, and the photograph of the project actually summed it up really well. It was really amazing. So now I will share regarding the new advancement that we are having in the Civil NX. So I will directly open the model that you shared with us on the new Civil NX to share you the new features that we have in the program. So I will share my screen now. Okay. Yeah, so this was the model that was shared from your end. So as you can see clearly that the user interface for the Civil NX, it looks a bit different than the existing Civil. So the icons and the arrangement of the menu, you will find that the icons are now been vectorized. And the point is, it's like if you are using the higher resolution monitors, so these icons will not be distorted. So now users can have the complete resolutions for their monitors as well. These icons will be clearly visible. And then if I say, so you will find that there are some other features. Like now you can add colors to your groups or any other, material or sections that you want. So what I meant by that is, let me just go to the hidden view first. Yeah. So here you will find the option of draw, and here you can find that in the element color, you will find that there are options for section color, material color, or element or structure group color. So if I click a random color here and click apply, we will find that as per the groups, so you will find the different colors of the element so that you will be able to recognize that, okay, this element is in a separate group and these elements are in a separate group. And it's a very, I would say it's a good way to have a complete different colors inside the base model only, so that you can have, okay, this is getting in a different construction state, this is getting in a different construction state. So yeah, so you can find these colors and change these colors as per your requirements. So another feature is that let's say this was a really big model and you have defined a lot of I would say pre-stressing tendons and a lot of other properties as well. So let's say if you want to edit any property, you can just simply search it down as well. So let's say if you want to go along with the, yeah, so let's say there is a tendon profile you want to edit. So currently in civil, you will go manually and find that tendon profile. And now you can just simply search it down and you will get whatever the result you want. So that's how it is easy it is for now. So we have a search menu inside the tree options. And another advancement I would like to share in the UI feature is this search option here as well. So here you will find that uh, whatever the help or the functions that you require in the civil, you don't have to go manually and find them. So what, let's say I want to define the beam and releases. So I just search beam and here. So you can see that whatever the functions that are provided inside the civil are going to be listed inside this search option, and also whatever the online helps, tutorials, or whatever the FAQs that we have regarding these. So all this will be listed inside your model only, and just click once and you get back to the Midas site, and you get all the help that is available on the web. So let's say if I want to define the beam and release, so you can see that on the left, whatever the functions that are available in the program. So you will be able to get them directly. You don't have to go into the ribbon tab and find those function manually now. Yeah, so another thing, the change is, yeah, so let's say you have some loading. So you have your loadings inside this tab. Okay. Yeah. So let's say if you have some loading displayed here. So yeah, so here you can, what you can do is you can change the scale and the label of that scale directly from here. So yeah, so let's say if you want to change the, label, you want to see the labels as larger, so you can completely adjust it here. And if you want to see the font size differently, or let's say if you want a bigger font size, you can change that font size from here as well. Yeah, so this was another upgrade that has been added in the recently in the new Civil NX. So I'll go back and I will go back here and let's say reset everything. Yeah. So now another feature is regarding the transparency. So here we have a feature of transparency. So let's say you are into the hidden view and you want to see your elements and you want to see your tendons where exactly it is passing through. So what you can do is you can press transparent all option here, or any other element. If you want to transparent, you just need to select and then press the transparent. So it will transparent only the selected option. So now you can control this opacity of those elements directly here. So what I meant by that is, yeah, you can see that these elements are now transparent in nature. So what you can do is just press, go to your tendon profiles. Come on, where are you? Yeah, here it is. So let's say this is the tendon profile you want to see. I will just quickly select this part. Yeah. So you will be able to exactly find out exactly at which location this tendon is going through. So this is another advancement in the UI feature. So now another thing you will find here is in the apps option. So what you will be able to find is that API option is added on now. So to connect to the API, what you need to do is either just simply press connect or just go to the API settings and press connect. And here you will find a MAPI key. So let's just connect it once. Yeah, so as soon as you connect it, you will have this disconnect button on. So you have this API key. So this is the identification of your PC. So what you can do is now you can connect through various apps. So I have another presentation for that. So before that, I would like to share this plugin option as well. So what these plugin options are, these are the added on options to the existing civil features. So what you can do is go to the marketplace here, and here you will find the various plugins that are added. So let's say plugins like group pile or alignment generators, or let's say played peers. So if you want to have a additional feature inside the civil, so now there is no restrictions to the users. that our developers has to develop it. So what they can do is also create a own plugin in the JavaScript language, and they can upload it inside the Midas Civil. So you can just upload this plugin inside the Civil, and you can avail the different features. Let's say if you find that okay, this should be in the user interface, this feature should be added inside the Midas Civil. So now you are not limited to our developers to keep on requesting, and then they will update it or not. But now you can just simply have that development from your end as well, and that power is given to the users as well. So you can have different updates as per your requirement. Additionally, we will be providing plugins every each 1 or 2 months, and this marketplace will keep on increasing. So you will have additional UI improvements inside the plugins as well. Yeah. So another thing is regarding the presentation I was talking about. So this is regarding the API presentation. So I would like to discuss what exactly the Midas API is doing and what type of API it is. So yeah, so let me just go to my presentation view. Yeah. Yeah. Okay. Yeah. So so Midas API will be working on the REST API form. So it's a RESTful API. So which means that it is working on a JSON format. So whatever the data you want from other apps, it has to be in a JSON format, and whatever the data that Midas will be exporting, that will be in a JSON format as well. So API technically means is application programming interface. So it is the interface between the different application. It is a way of transferring the data from one application to another application. So if you want to transfer the data from, let's say, Python, Excel, or even let's say Grasshopper, so technically you just need that data in a JSON format. So if you have that JSON format exporting from that source or application, you can directly add that file inside the Civil NX. And then in the same way, if you want to export that data from the Civil model, let's say the results or the images, so you can have that information inside the other applications as well, because these packages or most of the packages can read JSON. So another examples for these RESTful APIs could be, let's say if you are using an Uber app, you get a live location of the driver, right? So Uber doesn't have a navigation system of their own. What they do is they take the data from the Google. So they have that Google API. So they get the live data from the Google. So you can think of this as Grasshopper and think of this as Midas Civil, and you can have that live connection just like that. And similar way, our weather app in the Apple, it takes the data from the various sources in a live manner. So it takes that data, and Apple doesn't have their own weather station, so it's just not their business, right? So what they can do is they can extract the data from these apps or applications or websites, so they can put it directly inside your phone. So this is what a REST API does. It gives you the live connection, and it works on the HTTP method, which is get, post, delete, and put. So quickly defining these terms is post is like creating the new resources. So if you want your Grasshopper model or Excel or Python to create a new property inside the Midas Civil, you will be using this post command. And then similarly to read the existing resources. So just say you want to get the results. So you will be using the get resource, and then you will be using the put command to update the existing resource, let's say boundary condition or anything. And let's say if you want to delete anything in the model, you will be using the delete command. So that's what an API is doing. So you must be getting that clear picture that all these four features will be enough to update everything inside the model and get every information inside the from the model. And then, as I mentioned, all these packages actually read the JSON format really well, because they have the additional modules for the JSON. And if they have the modules, then as you can imagine, they can be connected through the Civil NX. So similarly, we will be launching the plugins for the Grasshopper as well, which will be helping the Grasshopper to extract the data in the JSON format directly to the Civil NX. So I have some videos for that as well. So firstly, I will like to share what exactly can be done through the Excel VBAs. So there is that video here. Yeah. So here what we can do is we can just input some parameters for the model, and then you just need to connect to the API, and then you put the map key inside here. So there is a background, I would say macros or a VBA code that is written. So this is getting connected to all these parameters, and then it is sending the information inside the Civil NX. So you can check that with this parameters, you just simply press a command that create model. So it will transfer all the data to Civil NX. And then if you can see that in this VBA example, we defined all the construction stages as well and everything inside the model. Inside the VBA only. And then if you press the analysis button, there is an analysis command that reads for Civil NX. So we can just assign another macro to that that will execute the analysis command. So after the analysis, what you can do is go to the results tab and use the get command to get the results. So you can get the results table. There is another macro in a way that is running this code. And then similarly way, you can get the result images as well. So I would say your Excels now can be directly linked to the your Civil NX model. And the best part about this connection, I feel, is there is no need for be on the same PC. So this Civil NX can be inside UK, and this Excel functions can be going inside India, Poland, anyway. So that connection is a server-based connection, so you don't have to be on the same PC for that. So this is what I like the most regarding these connections. Then if you go to the Python type of connections, so we can use languages like Python to get various sort of automations done. So such example could be the optimizations of the section. So let's say if you have a beam section, this is just an example, and it can be scaled up to any other bridges. And let's say if you have a beam and there is a stress value for a particular load that is coming on that, and you have set a parameter for a stress limit. Now what you can do is until your section is reaching that stress limit, you will keep on increasing the depth of the section. So in this video, that process is being described. So you have defined a, I would say, parameter for a stress limit. And then what you can do is press do analysis command, and then you will be getting the stress value. And until you get a stress value which is under the limit, your function will keep on iterating the process of analysis. So as soon as you reach the, I would say, the stress limit value, then the code actually breaks itself, and then you are getting out of the loop. So this type of optimizations can be easily done using the languages like Python, and you can check that now. This is not just limited to one single beam. If you have a bridges like, I would say, truss bridges, or I would say that arch bridges or cable stays, where the the weight of the sections are really governing the design sometimes, and then you can just simply reduce those weights by doing the optimization of the sections. And then if I show you regarding the link with the Rhino Grasshopper, so there is another example for that. So here we are having some plugins that will be launched. So we have this as a technical support as a beta tester, or you can say as a beta version of that. So what you can do is you can find that in these using these plugins, you can define almost all the parameters that are inside the Civil NX, and you can just simply put these parameters inside your Grasshopper script, and you can play around with these parameters. And similarly, we have a parameter for the API settings like the map key and all. And similarly, we have that for the Midas update option. So you can have that real-time update as well. And this was the beam command for the Civil NX, and then it takes the line like curves, and then it generates those lines inside the Civil NX. So now I just copied down the map key and then put it inside my variable or the panel for the Grasshopper, and then you can just, let's say, another script I prepared is for the grillage model. So it works as per the skew angle, and you can increase and decrease the element lengths. And then you can increase the span as well. You can increase the girder spacing, decrease the spacing. And another thing you can do is increase the number of girders. And also, I was trying to update the radius as well. So radius plus Q is a, I would say, difficult problem to handle. I'm working on that currently. And then, yeah, so now you can just simply update, because that line-like curves are directly connected with through the beam plugin for the Midas. And now I can just plug in the cables inside the, name and the key. And then the similar thing I can do for the steel property that need to be defined. Yeah, so now you can get that. And then if you press the update button here, so all these material properties will be defined here. So I just kept it as real time as false through a Boolean toggle. Because I don't want, if I make any small change, that directly reflects inside my model. That control I wanted for me, but if you want, you can have that control for you as well. So I just, if I press this button here, the whole data will be transferred back inside the Civil NX as well. So as you can see, there is no need to create any files or anything. This connection is just live connection. You can, on the background, the program is creating a JSON script, sending it to the Midas server, and the data is showing inside your model. So this, as I mentioned before, this model can be anywhere. This Grasshopper script can be anywhere. It doesn't have to be in the same PC. So anytime you just update the skew angle or span or number of girders and press the update button again, and you get the updated model as per your need. Yeah. So another advancement is regarding the Excel add-ins. So what this is the additional features. Add-ins are additional features for the Excels. So there are many other add-ins like ChatGPT and all, which we usually use inside our Excels. So what we can do is we can also add a Midas add-in as well. So Midas has provided its own add-in for the Excels. So what it can do is it can connect through your model and take out the results directly. So there is another example video for that. Yeah, so let's say if you have a structure inside your Civil NX and you have an analysis and you want to take back the results. So again, I will do is connect through the API, copy the map key and put inside my Midas connector. Before that, I need to log in. Yeah. Okay, so after the login, it will directly show you. Okay, this is connected now. So now what we can do is copy the map key here and then put it inside the setting options. Yeah. So if you press check here, it will be showing that it is connected. So now you have a connection between your Excels and your Civil NX model. So now you just need to do is either you just save the models, or also there is an option to directly write a small JSON script for each type of table that you want. And you can directly get that table inside your Excel file. And also if you want to take out the result images, so you can have that option available as well. So here you can just save that view beam image, let's say give any name, and then press the linking of the cell that you want to place your table or image. Just press add to folder and then press import. So as you can see that this is saved as a dynamic report table. So any change that you are doing inside your model, which will be reflected in these tables, and any change that you are doing inside the model will be reflected back inside the images as well. So let's say if you have all the images stored for the loads or any other views or any other load combination result, so all those images can be stored dynamically, and you don't have to copy paste and then take the use the stripping tool and get the screenshot again and again. You can have that directly inside the Excel file direct in for your model. So you can imagine that you can directly link this to your I would say design sheets as well. So you can have some I would say cells linked to the formulas for the designs, and then you can directly import these tables, and you can have all those automations done for your designs. So yeah, this was the plugins features. So I was mentioning before. So there are some use cases for these plugins as well. So this is the alignment generator plugin. Yeah, so as I mentioned before, you go to the plugin tab and then find the alignment generator plugin. So as soon as you press here, and you can run this. And there is some informations given how to use this plugin, and there is a short video for that as well for the tutorial. Yeah, so as soon as you press run here, so this plugin will be open. So now you can just give the length what you want to define for the alignment, and also you can provide the number of segments. So here, let's say you have 4 segments or 4 type of alignments that you want to define. So you will press plus 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 to add additional alignments, and here you can find that you can define the various type of curves like arc, lithoid, or cubic parabola. So all these type of curves can be defined, and you can control the element length as well here in the segment tabs. So that control is also given to you only. Yeah, so initially we can just simply define the alignment, and then if we press the create button after that, so the whole alignment that we have defined will be generated. Yeah. So here on the left on the tree menu, you can find that the node local axis as per the curvature is also defined. And if you can just now define the material and section properties, you will be good to go for your modeling. And another interesting plugin that I found is regarding this uh, concept modeling of the piles. So if you have a group of pile that is being modeled, let's say a mesh of or a mesh of 2 x 3 of piles. So you can just simply define using this plugin. So you don't have to copy paste all those piles as per your requirements and get the perfect location. What you can do is simply define the sections and define some boundary groups for your pile and pile cap, and then go onto the pile array option and select what is the pile array that you want. So let's say 3 x 4 or whatever. Then you can just select the spacing that you want between the piles, and then you will give some parameters for the pile cap. And if you press create here, after selecting the last node of your pier or the top of your pier cap, sorry, pile cap. Yeah, so here you will get the exact uh, array of the piles and pile cap that you wanted. So you don't have to manually define all those nodes and create the links between the pile cap and the piles. So that will be automatically done using your uh, Civil NX plugin. Yeah. Okay, so that's all that I wanted to share regarding the new developments for the Midas Civil NX. So the whole motive is to connect more and create more. So I hope you liked the developments regarding this. So would love to have your comments regarding that as well.
So that's all for the today's webinar. If you have any questions, please feel free to ask. Yeah. So thank you, Andrea and Manoj, for the presentation. It was a really informative information, and yeah, the webinar was really great. So I think Manoj and Andrea have already answered a few of the questions while we are presenting. So if you have further questions, yeah, please feel free to ask, and we are happy to answer all of the questions. Why everything is Yep. If you have no questions, maybe we can end today's webinar. And just before ending the session, yeah, just to remind you again, we are currently having a special promotion for the end of first half until end of June. So there's some offer for Midas Civil NX, or any other products from Midas. So if you need any product, if you're looking for any products at the moment, yeah, feel free to reach out. And also, especially for UK clients, we are visiting UK during 4th to 13th of June to provide some free face-to-face technical CPD sessions to our clients. So yeah, if you need any trainings or consultations, feel free to reach out. Here's my email address and my number. So yeah, okay, I think that's all for today's session. Thank you very much. And once again, thanks Andrea and Manoj for the awesome presentations. Thank you very much. Have a great day. Cheers.